students, we will discuss about the measurement of output power of a turbine using brake drum dynamometer. This photograph shows a reaction turbine. This is the reaction turbine. The turbine converts water power into mechanical power. So the output of the turbine is a mechanical power. We want to measure the mechanical power output using the brake drum dynamometer. So the brake drum dynamometer contains a brake drum which is rotated by the turbine. When the turbine shaft rotates, the brake drum also rotates because both are coupled together. Over the brake drum, a rope is wound as shown here, and the end of the rope you have a pan. Over the pan only we have to place the dead weights. The other end of the rope is connected with the spring balance. So this is spring balance. When you place a dead weight, when the turbine is running, a braking force is applied over the brake drum. The turbine has to overcome the braking force, and we are measuring the output power using this arrangement of brake drum dynamometer. The formula to be used is 2 pi nt by 60,000, where n is the RPM and T is the torque. The torque is measured by measuring the weight which is placed over the pan and the weight of the pan and the spring balance reading. If T0 is the weight of the pan, T1 is the dead weight placed over the pan, and T2 is the spring balance reading, the net force acting at the turbine is T0 plus T1 minus T2. And since the torque is the force into perpendicular distance, we have to measure the perpendicular distance at which this net force is acting. The perpendicular distance is the sum of the radius of the brake drum and the radius of the rope. So RFF, effective radius, is the radius of the brake drum plus radius of the rope. So if you substitute all these values in proper unit, the torque you will be getting in Newton meter. So when you substitute the torque in this formula, you get the output power in kilowatt. So this is how we measure the output power of a turbine using a brake drum dynamometer. If you read the nameplate detail of a turbine, you will have rated power, you will have rated speed in addition to other details. We want to measure how much maximum load that can be placed over the pan. We can use the same formula, 2 pi nt by 60,000. The rated power value is substituted from the nameplate detail. So for example, 3.7, it can be written here, and the unknown here is the torque. The speed also written on the nameplate detail. So when you substitute everything, the torque value is the unknown value that can be found out. The torque is sum of T0 plus T1 minus T2 into R effective, as already discussed. So here we can substitute spring balance reading as 0, and we can able to find out the value of T1. So the T1 is the dead weight to be placed on the pan to run the turbine at its rated output of say 3.7 kilowatt for example. So suppose if you get a weight of 10 kgf, when you place a 10 kilogram force of weight on the pan, you are running the turbine at its rated output of 3.7 kilowatt. Suppose if you place 7 kilogram force of weight, then you are running the turbine at 70% of the rated load. If you place 5 kilogram force, you are running the turbine at 50% of the rated load.